Uh, Let me first thank the organizers for giving me opportunity to speak here. Some of the things, and I might be able to answer some of the questions that were raised, not in the context of Aubrey-Andre model, but in a more simpler context, like what happens when you have many baths and so on. That's the kind of thing we have been looking at. So I'll talk about Keldysh field theory for open quantum systems, and we have three results basically. One is that depending on your bath, you can have very non-Markovian dynamics, and where does that show up, and so on and so forth. Second, localization. Let me give you what I mean by that. If you actually couple each site to a bath and then set up a voltage difference in the baths, then what you get, even in a simple model, nothing like Aubrey-Andre model, is actually localized current. The current decays exponentially with the size of the system. So that's the localization I'm going to talk about. And these two works would be on essentially non-interacting systems coupled to baths. And in the last part, if I get to that, I'll talk about what happens when you have interacting systems. In that case, I'll take a more standard ohmic bath. But I will talk about what happens when what does the interactions do? And we will see some old ideas of quantum jumps and Wigner's quasi-probability distribution make their appearance in a different form within the Keldysh field theory. Okay. So this work has been done with my student, Ahana Chakrabarti, who is here in the audience. So if you have more questions, you can later talk to her. Okay, so this is a brief outline. So I'll talk about a very brief introduction to Keldysh field theory, mostly to set up things that I would need. It's by no means any exhaustive thing about Keldysh. Then we'll talk about non-interacting bosons coupled to a bosonic bath. And here we will talk about non-Markovian dynamics and localization, the two things that I talked about. And then effect of interactions, where we will see that there is some universal distribution of quantum jumps, which comes out in some low energy limit. Okay, so just to start with the basic Keldysh field theory, mostly there in what I'm talking about is mostly there in textbooks. So what you get is you start with a density matrix and its time evolution. And then you realize that you have two things, U, which is the time evolution, and then you have a U dagger here, each of which you can, of course, write in terms of a path integral. So you have a forward contour and a backward contour, and you have fields plus and minus. Of course, only the sign changes because you're reversing the direction. It's basically U going to U dagger. So essentially, you can write down a path integral in terms of two fields at each space-time point. However, there are some more things. You might think, oh, this is some independent uncoupled fields. That's not true. One thing that you need to satisfy is at very large times, the plus and minus must be equal. So that's a boundary condition for the Keldysh field theory. And when you go to very large negative times, you have some density matrix you started with. And the matrix element of this density matrix will start coupling the plus and minus fields. This will come up as a boundary term. You have to be careful in formally just skipping it for some time until you get to propagators and so on. But modulo that, these are the two things that immediately couples the plus and minus fields. Of course, interactions, baths, and everything else will give rise to more and more couplings and so on, corrections to this. Okay, so then as I wrote down, you have a partition function, which is in terms of this phi plus and phi minus, and this dot dot basically tells you that you should have additional terms you should keep track of. And then you can do whatever you do in field theory. You can put sources on the plus and minus fields separately. Then you can calculate all sorts of correlators by taking derivatives with respect to sources. Most of the things that you do in a standard field theory then kind of goes over here with the fact that you have two kinds of sources and so on and so forth. Okay, so now why is this a good thing for open quantum systems? Because density matrices are obviously natural starting point for open quantum systems. Even if you start with a pure state, you might end in a density matrix. So it makes sense to start with a formalism which starts with density matrices. There's no adiabatic ramp up of interactions needed when you go to interacting field theories, unlike standard field theories, which means it can be used for studying non-equilibrium dynamics. It makes it possible to treat effects of dissipation. It's very hard to treat effects of dissipation if you have just one set of fields. You will see that dissipative terms come out as some boundary terms, but not in the once you have two kinds of fields. And of course, this is a rich history of having been used in quantum transport theory and to treat disordered systems, but we will not go there. We'll stick to open quantum systems and how this can help us understand them. I mean, so the idea is that usually what you would do is you would like to measure observables, which means you will put sources. So then wherever you measure observables, these two things do not need. But in the very large end, you have to identify this. Basically, there's one path integral, so you have to identify the fields at the end. And the consequence of, so most of the things that we would do would, when you start from that boundary condition, that boundary condition will go to infinity in that sense. This will basically prescribe for you what kind of regularizations you do, I eta and stuff like that. Essentially, that's the stuff that we go here. Okay. Okay, so now it turns out that it's much easier to work with a symmetrized and anti-symmetrized version of this field, and you will see why. Many things become zero. You can keep track of things easily. So then you just write a generic quadratic action. Suppose I'm doing non-interacting theories, where you can write some classical quantum field. So it's a two-component field now instead of plus minus. And there's a generic inverse Green's function that is sitting here. However, one thing immediately jumps out when you go to this is that the classical component of this must be zero. And this must remain zero. So if you take an action and you set the quantum terms to zero, only S of phi classical must be zero for all interacting cases as well. If you take a simple example, you can see that these two propagators are nothing but retarded and advanced propagators. They know only about how things propagate. Whereas this object, sigma k, actually knows about this density matrix and it knows about distribution functions in your hill. Okay? So if you go here, now if you go try to invert this thing, you go for Green's functions, which is the correlation functions that you're going to measure, you see that the classical part is finite, called the Keldysh component. These are advanced and retarded components. And the quantum part is zero. That's just comes from the structure of the inverse Green's functions. You have some more conditions that this GR and GA must be dagger of each other. This is upper triangular and lower triangular matrices. And there's this crucial thing that GR locally, TT plus GA at TT, must be zero. This ensures certain commutation relations are kept correct. Okay, and the Keldysh component is an anti-Hermitian object that is sitting there. So immediately you can see that if you want to do dissipation or so on, you have built into your theory things which might basically get into that one. Okay, and this is the last thing about formals before I jump into the actual problem. Since you have Green's functions and inverse Green's functions, you have a Dyson equation when you write it in terms of self-energies. The important thing to note here, the only thing to note here as far as we are concerned, is that when you take the retarded or advanced Green's function, it can be simply inverted like a normal matrix with the inverse Green's function. The Keldysh Green's function is, however, comes out to be GR sigma k GA. So one thing that you would know is that if you know the Keldysh self-energy and you know the retarded Green's function, and this we will use very efficiently later on, it's much easier to calculate the Keldysh Green's function because that's just a convolution or an integral that you have to do. Okay, so GK, of course, is directly related to the densities and currents in your system. So that's what we will be after in various points and so on. So we'll see. So this basically, this is my brief introduction to the Keldysh field theory. I've just set up things that I need to use later on. Now let's jump into this question of non-interacting bosons coupled to a bosonic bath. Manas's system would be one of them. We will not go into Aubrey-Andre, more complicated. We'll stick to much simpler things, okay? And so why do we want to do this? Of course, this is an age-old question of how quantum systems equilibrate, how statistical mechanics emerge out of quantum mechanics. And over the course of this conference, we have had a bunch of experimental realizations that people have talked about, so I'm not going to go into detail. In fact, I'm going to go and work with a model which probably you wanted to see what is the answer, which is I'll basically think of n systems, each one is coupled to its own path, and then they are coupled between themselves so that things can move from one system to another. Okay, so we are interested in large number of degrees of freedom connected to multiple external paths. So let's look at the model. This is a model Manas had actually towards the end talked about this paper where they had done a very extensive study. It was the same model that they used. So what is the model? See, the model is that these are sites. I have bosons on that site, and they're just hopping. It's a free bosonic model. Particles hopping on a lattice with some amplitude g. Each one is coupled to a path, which is also like a linear chain. It's coupled at the end of the linear chain. It has some scale TB, which will give you the bandwidth of the path. Okay. Each path can be set to its own temperature and chemical potential. Linear coupling between systems and each site with a band of the path with a coupling strength epsilon. So this is the simple model that we would like to understand and ask what happens out of this. Okay, so in principle, S can be more complicated stuff like optical cavity, Josephson junction in the fermionic version, quantum dots, etc., etc. But for the moment, we'll just treat them as one bosonic mode. Okay, and for reasonable things, both G, the bandwidth of the system, and the coupling should be less than the bandwidth of the path, because I was sort of surprised to see in the literature people have actually looked at things where the path bandwidth is smaller, but then that's in no sense a reasonable path if I can't absorb all sorts of energies in the system. Okay. Okay, so the usual thing to do is to first diagonalize the path, go to the eigenbasis of the path, then you will write it in terms of the eigenmode operators of the path, the system path coupling. There'll be some additional factor that will come as a weight of eigenvector. And hence, you take all of these, all the paths will be essentially determined by what is called the spectral density, which is this object square times the density of states, and so on. Okay, so assumption, of course, path is much larger than system, no feedback, and we are interested in steady-state dynamics in this system. So now you might think, oh, this is straightforward. I mean, why are you doing this? But we'll see there are some surprises. So let me just set up the Keldysh field theory. There will be a non-interacting quadratic action for the system, which will look like this. It's very simple quadratic action. There will be a path quadratic action for each path. Again, I've gone to the diagonal basis, so this is just omega minus omega alpha. And the paths, Keldysh-Green's function will know about the distribution function, temperature, and the chemical potential in the path. And the GR or A is independent of which path. So basically, we are coupling the same kind of path, but with different temperature and chemical potential. Okay, and then you can write down the path system path coupling. Again, it's all not that hard to do. So the point is, this is quadratic in path field, so why don't we integrate them out? That's the standard thing to do. And remember, since I have a linear coupling, I'll still be left with a quadratic problem in my system degrees of freedom, so which means I should be exactly able to solve them. In fact, we will show you that this model actually has an exact solution, which we can find. Okay, so then we integrate this out. Once we integrate this out, we get additional self-energies. So this is now the inverse retarded Green's function of the system. The paths have given me a retarded self-energy. Remember, this guy is same for every site. Because the retarded self-energy only looks at the spectral function of the path, doesn't look at the distribution function of the path. Since I've coupled same paths, they're all same. This we will use later on. And then it will also give me a Keldysh self-energy, which is the path, but now it is proportional to the distribution function. So this object, of course, is depends on each site. And this is the whole form of this. Now, for this case of the bath, as Manas had also showed, the spectral density is nothing but 1 over omega over 1 minus omega over 2 TB whole square with a square root. Okay, so it's basically some bland thing which is going here, but we will see what it does. At this point, before solving this, let's just understand what the self-energies are telling us in the context of equation of motion, because that's another way people have talked about this, Lindblad or anything, and so on. So it may be useful to just look at this. And this part is straightforward. For the Keldysh self-energy, you will have to do what is called a Hubbard-Stratanovich transformation. So e to the power I, and then once you do that, you will basically end up with saying something, there's something like a source term coupled to the quantum fields, and then there is a quadratic part in terms of these auxiliary fields. So first point is, if you get something which is even in phi quantum, try to do a Hubbard-Stratanovich to get to equations of motion, if you want to go there, okay? So then if you take the classical saddle point, you will see that you have this is just the standard Schrodinger equation, then you have this sigma r t minus t prime, phi r t prime, times something which looks like a Langevin noise, okay? And the real part of this will dress up your dispersions, imaginary part of this would lead to dissipation, and this is some complex noise. The noise correlator is nothing but this Keldysh self-energy. So one way to think about these things is self-energies would simply give you, in one case, the dissipation kernel, in one case, the noise kernel. I am going to tell you what kind of non-locality. That's the next slide. Can you just wait and ask it after the next slide? So I'll just tell you what kind of non-locality I get in both this quantity and that quantity, okay? So if you do this, the retarded self-energy is just Fourier transform of j of omega. That's very simple, I times some theta function, okay? The j of omega that we have is simple enough that you can actually do this Fourier transform exactly, and the answer seems to be a Bessel function divided by t minus t prime. Now, why is that useful or important or interesting? First of all, it's a purely imaginary part, so it's a purely dissipative term coming from the bath, so no dressing in this case. But if you take this object and go to large times, you see you get a power law, and the Bessel goes as 1 over root t, so you basically end up getting a power law dissipative kernel. That's your first signature that you cannot probably do something very local. So here you see in both the retarded and the Keldysh self-energy. So if you do the Keldysh, it's Fourier transform of this, you cannot do it quite as easily as this, but you can still find out what happens at large t, and the answer is both of these fall off as 1 over t minus t prime to the power 3 halves. This is not RR prime, this is t prime. Yeah. So this is not telling you anything. Things are more or less local coming from the bath, because the bath is just coupled locally to the site. Yeah. But here you will see that there are memory kernels in both. So nothing is happening in space as such. Okay? Okay, so now you cannot coarse grain over time. Usually you have some cutoff scale, something going exponentially down. You coarse grain to obtain a Markovian dynamics. So this is essentially non-Markovian. There is no way you can write down a Markovian description of this system. Okay, it's the first interesting thing that came out of this. If you ask where the origin of power law tails is, it's basically the fact that your j omega is finite, and then there is things which are non-analytic here. And anytime you have some such non-analyticity, its Fourier transform will show up in sort of power laws. Things like how you get Friedel oscillations from singularities of polarizability or things like that. It's basically just a property of Fourier transform. Okay, so it's this non-analyticity that leads to the power law in the Fourier transform. Now you might say, oh, let me take a smoother function. But you see, if you have a bosonic system where you try to put a chemical potential, which means that has a number conservation by itself, its spectrum needs to be bounded from below. And you cannot have a bosonic system whose spectrum goes all the way to minus infinity. Which means, at least at one end, you will definitely have some non-analyticity, And so this kind of reservoirs where in a bosonic system you are trying to put in chemical potential, you will have ubiquitous non-Markovian dynamics. There are other possibilities. For example, you can have band edges, which is what this is. You can have Van-Hoff singularities if you are just having a band in, let's say, fermion or anything. For phonons, you can have things like cone anomalies, which will give you non-analyticities in the dispersion. In general, you can have problems like Kondo lattice, strongly interacting problems, where you get non-Fermi liquid. Okay, so the idea is that the long-time behavior is sensitive to the nature and location of the non-analyticity. In fact, in a way, if you take this as your probe, you can probably probe the singularities in the bath density of states. That's something interesting that comes up. So you take a two-site model, just go to the toy model to see this carefully, and you go to the Green's functions now, not the self-energies, because these are the observables. What you will see is that there are two parts. There are poles which come from the denominator, which will give you an exponential decay, which is all that would have been there if it was completely Markovian. But it also inherits the non-analyticity of sigma, so there will be a non-Markovian power law tail. And the crossover time scale, when it goes from this is on a log-log plot, so this is the exponential, this is the power law, can be computed by just looking at what is coming from each of these two. Okay, so you can look at GK. Again, the pole structure is inherited from GR and GA. There's some prefactor now which is temperature dependent. Crossover timescale is weakly temperature dependent in this case. Okay, so it's mostly coming from the pole structure of GR and GA. So even this will show up in power laws at large times. Okay, what about observables? So if you look at something like current, you don't see this, simply because it's a local quantity. In Fourier mode, it's all integrated all over frequencies, so you don't see this. However, if you look at unequal current time correlators like current correlators, etc., okay, they inherit this structure because they're nothing but products of Green's functions. And at large, so here is two plots for IT prime in the same system, where you are looking at what happens as you crank up the system bath coupling, and you see that you start getting power laws much earlier, but also the decay is of course faster simply because you have cranked up the system bath coupling. So this is what would happen as you crank up your system bath coupling in terms of some observable like current correlator, which can probably be measured from noise measurements. Okay. Coming to the question Prasanna raised, we can actually solve this problem for the full chain. There's an exact solution. So it turns out all you need to do is invert this matrix. You can invert this matrix in closed form. Right? Okay, some mathematical trickery, but that's what comes out as the full answer. And here is what I was telling you, that the GK is a convolution of GR sigma K GR, GA, which is GR star. Okay, so once you have got sigma K reasonably well, and you have got an expression for this, you can simply just do this, put it in Mathematica, and like in some time you would get the answer. Okay, it's not something for which you have to do a lot of computation. Hopefully this would be used, and one can then use these things to compute things which are more complicated later on. Okay, so now in the chain what happens? Suppose I set up this, and I have set up a fixed temperature, but I have set up a constant gradient in the chemical potential. And here is the current. This is not the current correlator. This is just the current as a function of x. And you see that there is some boundary things happening here, but this is a log plot, so you can see that there is a clear exponential which occurs, the current decays with distance, which means if I go to larger and larger distances, things will localize, essentially. So I believe the answer to what happens with two baths and what happens with coupling to many baths at each site is very different. Yes? This is, yeah, so on the links. Yeah, S1, S2, S2, S3, and so on. There will, of course, be a current flowing between these two. And there's overall conservation. Sure, but in general, in this case, you will just basically, this is not something that is, it's basically what you are saying, the things are flowing into the lid. And this length scale over which it drops increases with the temperature. which means if I go to very large temperatures, classical limit, then actually this thing stops and I actually have a steady current in this system. Okay. Oh, you're saying what happens if instead I kept the chemical potential fixed and varied T? The same thing would happen. Random T1, T2. Okay, so I don't know what happens with random T1, T2, but if you give me a profile, I can tell you what the answer is. For example, if I just take T1, T2, T3, etc., or something which is going quadratically, then I would see e to the power minus x square rather than. All temperatures are same, chemical potentials are different, but we can do the other one. All chemical potentials are same, temperatures are different and varying with some linear thing, and you will get the same kind of flux. Okay, so if you just look at the scale, you will see that the inverse scales with beta. So the localization scale is linearly. I mean, okay, this is not localization in the standard sense you think of localization. I would agree with that. But the scale over which the current would fall increases linearly with temperature of the baths. And again, if you look at current correlators, you will see the similar behavior. There is still a non-Markovian tail. You might, depending on what value of coupling you have, you might have to go to very large times to see that. Okay, so this is the summary of the first part. So there's non-analyticity in bath spectral functions lead to non-Markovian dynamics. Shows up as power law and dissipation and noise kernels. Green's functions and, for example, current correlators. Show both. There's an exponential decay followed by a power law tail. And the exponent is just controlled by the nature of the non-analyticity. It doesn't care about anything else. And in a bosonic chain coupled to individual bath, the current decays with the size of this system. So one thing is that this is very long-range memory kernels, but that doesn't seem to bother the system in just going into it. Now, let me just, I have maybe about 10, 12 minutes. Let me just ask a different set of questions, which is, what if the system was interacting? Okay, and I don't want to put both non-Markovian and interacting together. That's something that we plan to do at some point. But so we will take a Markovian ohmic, standard ohmic bath, but we will ask, what is the effect of interactions? And our argument would be, what kind of effective equations of motion can you get? And what do they tell you about various things? So we will, let's see what happens. So what I will do is I will straight away go with a real scalar field. So you can think of some string and so on, which is, will basically give you a real scalar field theory. So phi classical and phi quantum are the corresponding fields. And in principle, this could be coupled to ohmic bath. So I'm not going to talk about how to get rid of integrate out the bath. I will assume that that has been done. I will just incorporate the bath in terms of a dissipation and a noise at this point. Standard ohmic bath, so nothing. So, okay, so I will get a Keldysh self-energy, which as we said is a noise. This guy will look like the standard del T square plus grad square minus MR square. So if I forgot the grad square, this is like the harmonic oscillator frequency if I was just looking at a zero-dimensional system. Okay, and then there is a gamma del T. Just one thing, in retarded and advanced, it comes with opposite sign. But this is coming from bath, let's say. I mean, in principle, you can generate it through interactions, but I'm just going to put it in by hand at this point. So the equation of motion, as we said, is a standard one, the dissipation, there is a noise, and this is a Langevin noise. So this guy is nothing but the strength of the standard Langevin noise. Okay, so up to this, there's nothing it's the old problem. So now we come to what happens with interactions, and the way we deal with this is through diagrammatics. So if you write down the interaction as a phi-4 interaction, this plus and minus will tell you that you have something which is phi classical cube phi quantum and phi classical phi quantum cube. So all my dashed lines will mean phi quantum, all my solid lines would mean phi classical, and that's the notation. And so in principle, I will have this kind of Green's functions that I will write down. Remember, there is no quantum Green's function, so there is no line which is completely dotted. Okay, these are the rules. And then what we want to do is the following. What we want to do is we want to ask what is the effective action? Can we do a loop expansion for the 4-point vertex and so on and so forth? Okay. Now what you see when you go out of equilibrium is there are new vertices generated. I mean, we know what happens in a 5-hour theory, standard 5-hour theory. Okay. You just don't generate anything new. I mean, okay. Here, because you have more fields, the kind of vertex that you generate first is something like a phi classical square, phi quantum square. And if you wish, these are the diagrams that would, and plus some more that can generate this kind of coupling. Remember, these are all generated from microscopic couplings. So these couplings I had in my starting system. Okay, there's nothing to do with baths and so on. You give me microscopic couplings at the one loop order, I will generate for you this vertex, which is phi classical square, phi quantum square. Interestingly, if you go to 0 temperature and adiabatic dynamics, standard 5-hour theory, these three things cancel each other. It's a subtle cancellation, but so we are okay, we do get back the usual 5-hour theory in the standard ground state 0 temperature limit, but otherwise this will start getting finite values, okay? What you can do, once you have generated this guy, which is G3, just look at this, 2 quantum, 2 classical, then you can generate another vertex, which is phi Q4. And I'm only looking at 4-point vertices. I mean, in principle, of course, you can generate 6-point, 8-point vertices, but I'm only interested in 4-point right now, okay? And the important thing to note is all the diagrams would be 0 if G3 is not generated, which means that, again, in 0 temperature adiabatic ground state descriptions, these things don't occur. So one thing you would see is that G3 needs to be generated first. So if you are worried, it's basically nothing but a higher loop diagram. You can just compute it out of microscopic couplings, but you have to go to one loop higher. Now, okay, so you get this, but what is the meaning of all of this in terms of equations of motion? Again, we just stick to our standard idea. Even powers of phi q, you just try to do Hubbard-Stratanovich till you get to a naught power of phi q, okay? Because, okay, so then one thing that you might have noticed here when I wrote down is that all these couplings are actually imaginary, that you can show exactly. I'm not going to go into the details, but using the anti-Hermitian properties of the Keldysh and so on, you can show that these couplings must be purely imaginary. Okay? So is G4, purely imaginary. Okay, so now this, you do one Hubbard-Stratanovich, you end up with a source term, which now, however, couples to phi classical, phi quantum. It doesn't just couple to phi quantum. Okay, and it has a Gaussian kernel, which is from this zeta 1 star. This guy looks like a term which would be a mass term in your Keldysh component, okay, phi square, okay. So this is a noisy mass, or if you think of a harmonic oscillator, it's a harmonic oscillator frequency has a noise. Frequency is varying. In other contexts, people call it the multiplicative noise. So it's not, again, something new. It's basically something that has, at least classical statmech and non-equilibrium people have used this for a long time. And the equation of motion now has this, plus an additional noisy term, but which is proportional to phi xt, so it's a delta correlated Gaussian noise. So if you go back and ask, what is G3, this coupling, doing? It's nothing but the strength of this noise, which is the multiplicative noise. So what you are generating is a different kind of noise. It's Gaussian, delta correlated, and its strength is given by G3. There I didn't have any interactions. I had a quadratic theory. You need all these nonlinearities to generate any of this. Because of interaction. 5-4. I've just added a dagger AA if you wish. I've gone to real scalars, so it's not exactly, but we can do it for complex scalars as well. But just local, Hubbard type, or just in field theory language, I've just added a lambda 5-4 term. I'm working with scalar, real scalars, so not quite complex bosons, but we have done this for complex bosons and it works. Yes. So what you see is once you do this and then you do loop expansions, you generate what in Keldysh looks like interaction vertices, and just in terms of the field theory. If you track back a little bit, this will look like a different kind of noise in your equation of motion. Okay. Now this is okay. This is this noise has been talked about before. We are not the first to talk about this, but this is something that people have not talked about, and you do generate partly because you don't generate in one loop. Go to, if you're just doing loop expansions, you have to go to higher loop to generate this, but this is generated. So we can ask the same question. Again, it's even in phi quantum, so let's do the standard trick of going through Hubbard-Stratanovich. Fine, you get a Gaussian part here and you get a source, but it's still even in phi quantum, okay? So what you do is what is called a nested Hubbard-Stratanovich. You just do Hubbard-Stratanovich once more on this term. Then you get two integrals, and then you finally get something which looks like a source term, okay? You have complicated things sitting here. Importantly, on a technical note, this is one case where you cannot leave out the prefactor. Usually when you do Hubbard-Stratanovich, you don't care about the prefactor, it's a number. Here the prefactor involves this field zeta 2, and of course our final goal is to integrate out zeta 2. So if you miss this factor, you will get into trouble. Okay, so you have to keep this prefactor in this case carefully. And then you can take all the zeta 2 integrals into something where you call f of zeta. Remember, there's a zeta square over zeta 2, okay? And there's a zeta 2 square over G4. So all of this goes into some f of zeta, and we will talk about what f of zeta is. Now, if you do the saddle point equation, you will basically tell me, oh, this is nothing but just what looked like a Landsberg noise. It's an additive noise, except it has a non-Gaussian distribution, some distribution. We'll see what it looks like in the next slide. Okay, so up to all fourth order, all 4-point vertices, the general structure of your saddle point equation of motion is coming out to be that you have one noise, everything else gives you more noise. Of course, there are actually phi cube classical term coming from the standard nonlinearity term, which I have not written down. I'm just writing this. Okay, now, so the question is, what is f of z? Turns out that you can actually do this integral. As long as at least it's just locally acting. Okay, up to something you can work out. It's given in terms of some hypergeometric functions. What is interesting is when you plot it. So first of all, there's a universal distribution because you can show that in terms of RG, anything else will have derivative terms, so they will be irrelevant. So if you go to low enough energies, this is the only phi quantum 4 term that would remain in your system. This is characterized by a single parameter, G4 in our notation, okay? And the distribution is negative for some values of zeta, so it's basically not a proper probability distribution. This goes back to old work by Wigner and others when they were trying to formulate quantum mechanics, quantum in terms of phase-space distribution functions, and they came up with things which could actually be negative. But by the way, remember that up to this G4, if you scale Z over G4 to the power 1/4, this is a completely universal function. I can tell you how much its width is, how much negative you have, and so on and so forth. Okay, so this is clearly a completely quantum term with no classical analog. There is no way you could have written down a noise whose distribution function can become negative. Even more importantly, the first 3 moments of this distribution functions vanish, and the 4th moment is negative, which tells you that it could not have been a positive definite function here. Okay, so we get this final term which looks like basically a noise, but with negative distributions. This has been talked about in other contexts in quantum optics as quantum jumps and so on. But this, in this case, can be done for a generic field theory for anybody's systems. And in those cases, again, the distribution of quantum jumps is often put by hand because people don't know what to put in for them. They know certain things that, things like this should happen. In our case, there is a microscopic derivation, at least within a particular approximation, and which can be more rigorously justified by RG, that there is a universal form that you should put in. So let me just put up my last summary slide, and I think I'm already out of time.
So in this last 5-4 theory with the bath, so you integrated out the bath.
Yeah, I assume that there is a Markovian bath.
Yes.
I have integrated out, which means I just get a dissipation and a noise.
Yeah, so where was the dissipation? Because that's a bit...
I just put it by hand because, okay, so the dissipation would come in a, okay, so let's see.
Because it looked like there was only noise and it was a bit...
Yeah, and the dissipation comes in the quadratic part of the Hamiltonian, okay, so it's not going to be coming from any quartic terms. So this one. I just put it by hand. But in principle, you can do self-energy corrections to 2 loops. And in 1 loop, you don't get this. But in 2 loops, you can get the dissipation correction to this coming from interactions. I didn't focus on that because I was trying to focus on what the 4-point vertices are telling us. Yeah.
So in the first case, you had these power law tails in the current correlation.
Yes.
So it's non-interacting, non-Markovian.
Non-interacting, non-Markovian.
Did you have such power law tails in the interacting Markovian as well?
No. Interacting Markovian does not, because Okay, so there is some years of following. So all sorts of Green's functions are nicely regulated if you have a finite gamma. See, by choice, I have taken out any self-energies which have kernels. So that's by choice. I mean, I can do, you can ask me what happens with those self-energies. Why don't you put them in and then do what this? That's work in future, but okay, so what I did was, for example, I said I will only focus on the local term at the same t, which I can give good interpretations. That becomes iffy if you have power law tails. Here I can at least in some RG way justify those things. If I have power law tails in my Green's functions, then I don't think I can do that. I mean, I can still write down what the whatever quasi-probability distribution, except it will be some complicated, messy. It's not something that is nice and you can work with. Some complicated correlated distribution. I mean, it would not be independent distributions also. Right? There will be some Z1 at t, Z2 of t, whatever. All those things taken will give you some function. I don't know what I will do with that in this way of thinking. In terms of just doing diagrammatics, I can do. I mean, if I don't go into this interpretation business, I said, let's just do diagrammatics, loop expansions, let's do calculate self-energies and whatever. Then you do diagrammatics. Then you can still do all that.
I have a naive question. What happens to the fluctuation dissipation theorem when the new kind of noise terms come up? It doesn't change the gamma because first few moments are vanishing. Is that the correct thing?
Not quite. Okay, so the one that you should be more worried about there is the multiplicative noise. Because, for example, it is known if you just have multiplicative noise and you don't have certain other terms on the left-hand side, you don't get to the equilibrium, you get to what is called Salis distribution and so on classically, okay? However, there is some other work which shows that there are certain kind of derivative terms on the left-hand side that we have not been writing down, some derivative interaction terms, which will also be generated in the process. And then there is this idea that then it might still go to thermal equilibrium. One more point, all these terms, if I go to thermal fixed point at high temperatures, are RG irrelevant even in power counting. So presumably they all fall away before you go to high temperature thermal distributions. I don't know what happens at any arbitrary temperature, okay? And I can maybe do this and maybe do that. This is a self-energy, right? So this will basically give me something like phi quantum t some sigma tt prime phi classical t prime, let's say, okay? And then I can simply go to what is called the do derivative expansion. Basically, I write it as sigma t tau phi classic quantum t plus tau phi classical t minus tau, okay? If things are time independent, there'll be no dependence on t. But now I can do a derivative expansion on these fields. Okay, so there'll be one term which will look like, okay, so there's a dt d tau, presumably. Okay, so there'll be one term which will now look like phi quantum t, phi classical t, d tau, sigma t tau, something like that. But then there'll be terms like phi quantum del t, phi classical t, minus phi classical t. And this is how the structure comes out. This will be multiplied by something like d tau, sigma, t tau, tau d tau. Okay, things like that. So basically, this will look like a friction dissipation term. So there'll be renormalization of all of those terms that I have written coming from interactions. What I was focusing on, what are the new kinds of terms that are being generated? All of those gammas, m square, etc., will get their usual interaction renormalization because they will change. There will be a correction.
So, if your microscopic model is something like, okay, so let's say the 5-4 model, which has a well-defined classical limit. Yes. So, in the high temperature limit, I mean, you would expect that it should be described by a regular Langevin equation, right?
Yes.
So, do you recover that exactly? I mean,
so let me say the following. Okay, so if you do a scaling argument, okay, so if you try to do RG, for example, and you assume, for example, this object, which I said mq square over gamma, should go to temperature, right? And that this temperature is large and fixed, okay? Then you see that these terms are generated, but they're all RG irrelevant. So yes, you will get back. And there'll be some leading quantum corrections, that will always be there. Except as I go to lower and lower energies, they will be more and more irrelevant. However, if you are at quantum limit t going to 0, then these terms would start. They are marginal, at least in that limit. And then what happens in loops is the question.